Not all surfaces reflect light. Some do and some don't. Some surfaces absorb most or all of the light straight, and some reflect all or part of that light. And the way in which a surface reflects light determines how it looks to us. For example, the color, for one thing. If you have a red ball sitting here, the reason you perceive that as red is because the light shining on it, say the sunlight is shining on it, the sunlight that we call white light really consists of light of all different colors. When that light lands on the ball, all of the light is absorbed except for the red light. The light that is the particular wavelength, the particular frequency that corresponds to red is reflected off, and that enters your eye when you look at it. The red light comes into your eye, and you perceive the ball as red. All the other colors are being absorbed. And the same is true for any other color. If you see something that's blue, the reason it appears blue is because it's reflecting blue light into your eye. Now, if you're watching this video, you're actually looking at a computer screen, not a ball right there. And the reason this circle on your screen appears red is because it is emitting red light. That's not really reflection. So just pretend like this is an actual ball in the real world and light is striking it. The reason a red ball appears red is because it reflects red light. Now, whenever you have light coming in and striking something, the incoming light rays are called incident rays. So incident is just a synonym for incoming. So there's incident light rays, and I'll draw these coming in basically parallel. The sun is very, very distant, and in this context you can think of it as a point source, and the incoming rays are basically parallel. But when they strike the surface may appear smooth, but most surfaces are really rough on a microscopic scale. In other words, if you were to zoom in and magnify that surface, it wouldn't just be straight. It would consist of a lot of little jagged sections, maybe some flat pieces, but it's not at all smooth. And so the incoming light rays, the different rays striking different parts of the surface, are hitting different facets here at different angles. So some of these light rays are going to get reflected in some directions, some are going to get reflected in others. And the result here is what we call diffuse reflection. The light scatters. If the surface really is smooth, though, on a microscopic scale, like a polished piece of silver or smooth glass, then the incoming rays, which are all basically parallel, get reflected in a parallel fashion. And if you're watching this, if your eye is over here, this is your eye from the side. Okay, so that's your eyeball right there. And these would be eyelashes on top and on the bottom. So if you're looking and you're looking this way, you see the light enter your eye, you see a bright spot right down here where the light is striking it. This is called specular reflection. And we've seen a lot of this in everyday life as well. Here's a graphic that shows 5 steel balls in this room with some colored walls. And the ball on the right is highly polished and very smooth. You could see this, if this were real, you could see the one on the left for the same reason you could see anything, because light striking it reflects off. When we're studying reflection, it's often helpful to consider a single ray of light coming in and striking a surface. And we can represent that ray with a straight line. It comes in and strikes the surface at a certain angle. And the angle that it strikes at is called the angle of incidence. Now, it's important to remember that we always measure these angles relative to the normal. So take the point at which the light ray strikes and draw a line perpendicular to the surface at that point. And remember, the word normal simply means perpendicular. So that's the surface normal at that point. The angle here that the ray of light makes with the normal, that is what we call the angle of incidence. So the incoming ray is the incident ray, and the angle that it makes with the surface normal is called the incident angle, or the angle of incidence. And then the ray hits the surface and it bounces off. And this angle here is called the angle of reflection. The angle of reflection. And this ray bouncing off is, of course, called the reflected ray. Now, the law of reflection is very, very simple and intuitive. It simply says that the angle of incidence equals the angle of reflection. So this angle, the incoming angle measured relative to the normal, equals the reflected angle measured relative to the normal. And that fits with our everyday experience with ordinary objects. If you have a wall and you throw a tennis ball at the wall, it's going to bounce off. And the incoming angle, you should understand, and you should have experienced things like this, approximately equals the reflected angle. Some spin on the ball might change it a little bit, but the general idea is always the case. If you throw a tennis ball straight at the wall, it's going to bounce straight back. And if you throw it at a very shallow angle, it's going to glance off at a very shallow angle. Light rays work the same way. The angle of incidence equals the angle of reflection. Now we'll talk about image formation in a plane mirror. And by plane mirror, that's P-L-A-N-E, we mean a flat geometrical plane. So this is just a flat mirror. So let's imagine looking at a mirror, and this is the mirror seen from the edge. So this is the floor down here, and let's suppose that an object is standing on the floor right here. And then we're going to be up here, so this is our eye seen from the side. So that's the pupil there and some eyelashes. That's supposed to be an eye. So like if you're having trouble with that, imagine the nose and the mouth and the chin there. So that's a face. You're looking this way. So that's an eye seen from the side. Now, whenever you look at anything, you're looking in a certain direction. And when you look at an image in a mirror, you're looking in a certain direction. And light rays are coming from that direction into your eye. And the image appears to be in the direction in which the rays are coming from when they enter your eye. So what we see down here, I'm going to draw the light rays reflecting off the top corner and the bottom corner of this object. So this is a solid object down here, and light is coming in and striking it, and light is scattering off from that object in all directions. Some of those light rays come and strike the mirror and enter your eye. Let me try that one more time. Okay, and some light rays from the bottom corner down here also come and strike the mirror and enter your eye. So the point I'm making here is that when you look at the image in the mirror, if you look this way, you can see the image in the mirror, but your line of sight goes in this direction, follows the light rays coming into your eye. So if we take these two lines and extend them this way, we end up with a point down here and a point here. The object appears to be over here. It appears to be behind the mirror. And you should be familiar with that. When you get up in the morning and you look at yourself in the mirror, you don't see the image of yourself on the front of the mirror like a painting. It's not like it's right there on the mirror. If you're 2 feet in front of the mirror, then the image of yourself is 2 feet behind the mirror. In other words, the light here, look at this top corner. The light has traveled a certain distance and entered your eye. And you can perceive that. So you see in this direction, that far away would be this point in space right here behind the mirror, such that this total distance is equal to the total distance the light traveled before it came to your eye. And the same thing with the bottom corner. Light coming off the bottom corner goes a certain distance and enters your eye. And in that direction, for that total distance, you see the bottom corner of the box. So the image appears back here behind the mirror. Now, what's actually behind the mirror, who knows? This could be a wall, this could be another room, this could be outside of the house. The point to understand here is that there aren't actually light rays here converging to form an image. This is what we call a virtual image. No image really exists over here. Could be anything imaginable over there. But it appears as if the image is there. That's a virtual image. That's different from what we call a real image. A real image forms where light rays actually converge to make an image. And a good example of that would be a movie screen. If you have a movie screen here and there's a projector over here projecting a movie onto the movie screen, then light rays are actually shining on the screen. And there's lenses and a light bulb producing light and lenses focusing the light on the screen, so you actually get an image in here on the screen. Maybe it's some mountains and some sky or something, but you actually get light rays landing on the screen, producing an image on the screen. That's a real image, and it actually exists right there on the screen. That's why we call it real. A virtual image is an image that only seems to exist at that particular location. A spherical mirror is exactly what the name implies. It's a section of a sphere. Picture this curve right here as a piece of a three-dimensional sphere. And then these parallel lines are incoming light rays. And you can see at this point right here where this light ray at the top strikes, because of the angle at which it strikes the mirror, it's reflected down. And the same thing happens with this light ray. It's reflected down. And light rays down here at the bottom are reflected up. And just picture that same thing in 3 dimensions. Light rays are reflected all toward this region, which we call the focus. Now, a spherical mirror won't bring light to a perfect focus, and you can prove that mathematically. If you want incoming rays of light to come to a perfect focus, you need a parabolic mirror. So this curve right here is in the shape of a parabola, and this is a cross-section. So again, picture this as a 3-dimensional shape. It's like a parabola rotated about its axis. It's what we call a paraboloid in a math class. A paraboloid will concentrate incoming parallel rays of light to a perfect point. And parabolic reflectors like this are really, really useful. They bring these light rays in and concentrate them at a tiny little point there. Antennas are often made this way. The satellite dish antennas or direct TV or something like that, or dish TV, or any kind of large dish that's receiving a signal from a long way away. What happens is incoming light rays or radio waves, which are just a form of light rays, get concentrated. The antenna, the radio antenna in your car, or if you have a radio or a stereo at your house, the antenna, you don't need an antenna like this. The signal that you pick up is relatively close by and relatively strong. The broadcasting tower is relatively close by, presumably in your hometown, and you're listening to the radio. And the signal's strong enough to be picked up with an ordinary antenna. But if you're picking up the signal from a satellite in geosynchronous orbit, it's over 20,000 miles away. And by the time the signal reaches Earth, it's dispersed and is very faint. So what you do with a dish, something like this, you take all of the area that these incoming radio waves are hitting. So they're landing on that much area. So this much signal, this much of the radio wave ends up getting concentrated down to a tiny little point. And that's where you put the antenna. The dish itself is not the antenna. The antenna is just the wire or associated electronics placed at that point, at the focus of the reflector. And that takes the relatively weak signal and concentrates it, makes it a lot easier to detect. The same principle here of a reflection in a parabolic mirror can also be used to make a spotlight. If you were to put a light bulb right here, the light coming out would reflect off the mirror, and the rays would all go out parallel. And so you'd have a nice straight beam of light coming out. Now you'd also have some light rays coming out here that would spread out, and so you often see a wide circle of faint light and a bright spot right in the middle. Car headlights are typically made with parabolic reflectors like this, and a good flashlight or a spotlight in an auditorium would have a parabolic reflector. And a lot of times you can take the bulb here and move it back and forth so it gets a little bit off of the mathematical focus, and that would cause the light beam to spread out some. And so you could adjust the size of the spot that it makes by adjusting the position of the bulb. And if you have a parabolic reflector like this, you never get a perfect spotlight. These light rays never come out perfectly parallel for two reasons. One is it's impossible to manufacture something perfect.
Thank you very much for your attention.